going to assume, well, okay, we have an incline. We have something that rolls down the incline. The incline in general doesn't need to be straight. It could have rises and falls. It could even have a loop if you've got a track to keep the whatever the object is on the track. But in this case, we're going to assume that the incline is in fact straight. So we'll assume we have a straight incline, because I started to do this, and I don't know if that video will actually appear or not. It depends on whether I decide to keep it or not. But I got into this, and I got into the explanation, and I really couldn't go on. And the reason was not that I don't know how to go on. The reason is that if I went on with the assumption that this thing could have rises and falls, all of these products became integrals, and we're not yet equipped to talk about those integrals. So I was talking about the integrals without talking about the integrals until I just gave up and realized there was no way to do that at this point. So we have a straight line from here to here, and we have a net force that consists of the force, well, three forces. Okay, you have an object rolling down an incline, obviously you have gravity, and obviously you have a normal force. And there's also a frictional force. And we're told, well, okay, that's the situation. So there's our net force. These are all vectors. The net force, of course, will be in the direction along the incline, and that happens because the normal force does just what it needs to make that happen. And we have a frictional force in the direction opposite motion. If the object is moving down the incline, well, whichever direction the object is moving, the frictional force will oppose it. Now we're assuming a delta y down the incline. So we say that our F net delta S consists of what? Well, first of all, the frictional force times delta S, the normal force dot delta S, the gravitational force dot delta S. So you just have a distributive law here. If I expanded this, it would be this plus this dot delta S. Give you the same thing, and that clearly would be F net delta S. So clearly F net delta S by the distributive law allows us to expand and get these three terms. Okay, well then, F friction dot delta S. What is that in terms of the magnitude of the frictional force and the magnitude of delta S? It's just negative force of friction times delta S. Why negative? Because delta S is some distance in this direction, some displacement in this direction, and the force of friction is in the opposite direction. When you multiply two quantities in opposite directions, you get a negative. If you're doing a dot product of two vectors that are in opposite directions, you are going to get a negative multiple of their magnitudes. Okay, normal force dot delta S, what is that? Well, the normal force, by the definition of normal force, is perpendicular to the incline, and the motion is parallel to the incline, so that the normal force and the delta S are perpendicular to each other, giving us a dot product of 0, since normal force is perpendicular to delta S. And then F grav dot delta S, that's just going to be F grav, which is downward, and we're assuming that delta S is downward. We have a downward displacement of magnitude delta y, so that the magnitude of F grav is just F grav, and the magnitude of delta S is just, well, I'm sorry, so the magnitude of delta S isn't delta y. Delta S has an x component and a y component. When you dot F grav with delta S, you essentially, as we saw here for the same reasons, just pick out the vertical component of the delta S and you multiply that by the gravitational force. Since the vertical component, the downward component of delta, well, the vertical component of delta S is downward, gravity is downward, so we multiply the force of gravity by the vertical component of delta S. Vertical component of delta S is just your delta y. Okay? So we get F grav delta y, and it's again because delta S would be a delta Sx times I minus a delta y times a j, just the same as it was over here for the same reasons. And F grav is negative mgj. When we dot this with this, we get negative mg times your delta y, times the negative delta y, which gives you just mg delta y. So this gives us mg delta y. This gives us negative force of friction times delta S. So that now our work energy theorem, which says that delta F net dot delta S, which comes out to this, has to be equal to the change in the kinetic energy. So there's our result. If we know the delta Y and we know the frictional force and we know how far this thing travels under that frictional force, then we can get the change in the kinetic energy. If we know the initial velocity, we can find the final. If we know the final velocity, we can find the initial, assuming we know the mass.